So for example, if I do like 5 minus 3 equals 2, you know, opposite operations could kind of be like 5 minus what would give you 2, right? So you are taking something that you know how to do, or another example, 5 plus 3 is 8. So then 5 plus what number would give you 8, right? So you can add 5 plus 3 is 8, or you could do the opposite. 8 minus 5 gives you 3, right? Gives you back, right? So that's what we mean by opposite operations. And then you learn in like grade 8 and grade 9 how to expand, and you learn how to factor. We learn how to multiply. The opposite of that is divide, right? And we learn, let's see, oh, here we go. And then we learn about exponents. I think you do exponents in elementary school, you know, grade 7, grade 8, but in grade 9 you get into them a lot more. So 5 squared, we know that's 5 times 5, and it's equal to 25, right? So we know how to evaluate that. Now you can all evaluate this, it's kind of the same question, but what operation is this? If I move the question mark, so this is what I'm getting at. Like 5 squared equals 25. There's 3 places that I could put the question mark in an expression like this. If I put it here, that's the first one you learn. That's just evaluating exponents, right? If I put it in for the 25. If I put it in for the 5, what operation is that? It's like using a square root. Very good. So this would be like, so it's obviously 5, but this would be like the square root of 25 equals 5, right? So that is moving the question mark. And like to me, this helps me relate how operations are related to each other, right? This helps me understand how operations are related to each other. If I think about the expression that I learned first, and then I move the question mark to give some context to what a square root is. And if I changed the exponent, then I just change the number in the square root sign, obviously, right? So what if I put the question mark in the exponent? What's that? Good guess. Yeah, that's a logarithm, right? If that's the last place that the question mark can go. How do we evaluate that? How do we figure that out? In grade 11, you learned some of this. So in grade 11, you would probably do this. 5 to the x equals, and you would express 25 as a power of 5. So what exponent gives that to you? You just do that by inspection because you know your powers. And then we call it, is this familiar? Did you do this in grade 11? I think you should have. And this is called equating the exponents. So if the bases are the exact same, the exponents have to be the exact same. And you can do more complicated ones than that. It's an easy one. But solving these like that by equating the bases, by writing them with the same base, right? So you have solved these before, but not really with an operation, by inspection and by rewriting in a convenient way. Okay, so we do have an operation. And and so here to prove the point, this is one that we could do. So 2 to the x equals 32, which would be 2 to the 5. Therefore, x must equal 5, right, for that to be balanced. But what about the other one? 6 to what exponent would give me 100? What is 6 squared? 36. What's 6 cubed? 216. Nice. So it's somewhere between those two, closer to the 2 than it is to the 3. So I could guess that it's, I don't know, 2.3, 6 to the 2.3 or something like that would give me around 100. But that's not very accurate. Obviously, it's not that great. So our grade 11 skills work, when it's nice, when the numbers are nice, but not when the numbers aren't. Okay? So we call these things logarithms, and here they are. This is a notation. How do we write this? If nothing else, I think the most important thing for you to think of is the base defines the operation that you're doing. This is a bit of a tricky thing, but if I'm doing 2 squared, that's different from 5 squared. The base changes it because the base tells me what I'm multiplying by, right? And then if I change the exponent, that's how many times, but the base tells me what I'm multiplying by. So every base is almost like a different kind of operation. So my point is, the base defines what you're doing. The base doesn't change. It's the one thing that doesn't change between an exponent and a logarithm. Okay, so if I'm looking at this, what's the base in that first one on the left? This is a terminology thing that, again, we should have learned in grade 9. Like, what's the base? What's the exponent? What's the power? The 6 is the base. So if I'm writing this as a log, 6 is still the base, and we put the base for a log as like a subscript there. But remember, the exponent is our question mark. A log will evaluate to find the exponent. So the exponent goes there. I almost drew that as a question mark. And then the result of the power, which is 36, goes inside the logarithm. So you have to remember that this is the base. And if you do that, then you'll never write it the wrong way. Like, I think because it's a new notation, and you're so familiar with exponents and a lot of these other things, and all of a sudden logs come in and it's very new and it's just a bit different, that people forget kind of how to write them, and people forget what exactly it means. And to me, thinking about the base is really helpful. Okay, and so what would happen over here? So again, the base doesn't change, so the base is 3, and then the 4 and the 81 kind of swap positions. 3 to the 4 gives you 81. So log of base 3 of 81 is 4. In other words, what power of 3 gives me 81? Right? If I didn't know the 4, it's saying 3 to the what gives me 81. That's what a log does. Everybody okay with that? All right, so a little bit of practice rewriting these things. Rewrite the following in exponential form and then solve. So what did I just tell you? So don't use the function on your calculator. That will, like, if you have a calculator that can evaluate logs, it's not what you're doing. You need to get your brain wrapped around what a log is. And if you just punch it into your calculator and let your calculator do all the understanding, I don't think it'll work. So we're rewriting it, right? So the base doesn't change. And then just like grade 11, we can rewrite this. Okay, try the next one. Pretty straightforward, but try rewriting it. A, B, D. Is there a C? Oh, there is a C. just change the order. All right. So 3 to the x is 9. This is what people like to do who don't really understand this stuff. So then they go 3 squared is 9. This is the wrong. Therefore, x equals 2. There's something weird about this to math people. Like all of a sudden the x is missing, then all of a sudden it's back. That's not typically how we solve equations. So if you write it this way, this is not exactly what we're doing because we're really moving into logs, not doing the grade 11 part of it, but that's a common way that people write it. That's not the right way. Therefore, x equals 2. What about the next one? So again, the base doesn't change. So 4 to what exponent would give me 1 over 4? Anybody want to try that one? Sam? -1, nice. So there's our quick little, what's going on here? What's happening yesterday? Quick little reminder what negative exponents do. We haven't seen a lot of that. Okay, so this one's easy, so I'm just going to quickly solve it. Okay, so log to base 10. Base 10 is a common base. If you have like a calculator that's not a super fancy one, when you hit the log button, it's doing base 10. And you can't really change it. Like it might be possible, but it's hard. So that's a common base that we use. But once we get into this one day next week, that won't be a problem. Okay, so a base 10 log is a common thing, but base 10 here, if I rewrite this and I think about it, what do I notice for E? What power of 10 will give me negative 100 as a result? That's right, nothing. Again, a common mistake. People will put negative 2 in there. But negatives make them a fraction. So don't get confused here.
If you were moving it over, like, would you be able to move the 100 over and make it positive?
You could do that. 10 to the x plus 100 equals 0. But it still won't have a solution. But you could rewrite that, sure, in lots of different ways. But it still won't have a solution. Because you'd still have to get two things adding together to give you 0, and you can't make one of them a negative to make that work. Okay, and then the last one, again, the base doesn't change. Why did I put 2 there? It's supposed to be an x. So 1/3 to the x equals 1/3. How do I turn that into a 9? Negative 2, right? So it's going to flip it back into a 3. The negative exponent will give us the reciprocal of the base, and then squared is 9. Okay, pretty straightforward, I think. Any questions? Just notation, but get used to what a log is. Base doesn't change. Think about the base of the exponent, the base of the log. Learn to rewrite it. Try to get a sense of what it's doing. It's finding the exponent. 5 squared is 25. 5 to what exponent would give me 25, right? Okay, let's move on. What's the inverse of y equals 2 to the x? How do I find the inverse of a function? Do you remember how to do that? You did it a long time ago? Yeah. So x equals 2 to the y, but this is not how we write functions because x is by definition our input and y is our output, and I can't put x into that equation, right? So we would have to rewrite it. The base stays the same, so I get log base 2, and of x gives me y. So now I've rewritten it properly as like input output the way I would want for a function or for any relation, whether or not it's a function. Okay? So I think that the practice for this section wants you to kind of do both. Like it wants you to think about rewriting it by interchanging the x and the y, but then also how that would look using logs. So you have to do a little bit of both. And then the other thing is when we graph it, what does the inverse look like graphically? Lots of different ways to think about this. There's a particular reflection that happens, but then also you can interchange the x's and y's of the coordinates, and that will give us the inverse. So let's graph y equals 2 to the x. Then, do you remember how to do this from grade 11, we haven't done a lot of graphing exponential functions. The nice thing is, like, there's key points, so we're just going to think about the key points, almost like we're building a table of values in our head.
The y-intercept's 1.
Yeah, so 2 to the 0 is 1, and whether it is, I almost did this wrong. My scale is kind of funky here. So there's 1, 2, 3, 4. So 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. But usually you can't even fit those points on there. Okay, and then going the other way, I hope you're used to this by now. Like, we're not super sketching this for accuracy, but we're trying to get a sense of the shape. We want to know approximately what it looks like. 2 to the negative 1 will give me a half, right? Because it flips it. 2 to the negative 2 is a quarter. So I can kind of just think about the relationship and come up with a few points, and this is what the exponential graph looks like. We okay with that? So the inverse. This point is x equals 0 and y equals 1. So I go x equals 1 and y equals 0. 1, 2 becomes 2, 1. And on the other side, negative 1 and a half would be a half and negative 1. And I think I can get another point here. So this is a graph of y equals log base 2 of x. And where is the reflection? In that line, right? Y equals x. Remember how that's where the inverse is reflected in that line? Okay, one more. What about 1/3 x and its inverse? So this is one thing that's different about exponential functions in grade 11 and grade 12. Makes them different from all the other functions that you do, is that that's not a transformation. It's a change of base. It changes the function. When you change the base, you're changing the function. Right? It's not a transformation. So you can still have the transformations of these things where you have a vertical stretch or horizontal stretch or all of those things. Like, you can still have all of that. But this is a different kind of function. That's confusing. So when you're graphing these, because we graph all different ones, 2 to the x3 to the x4 to the x5 to the x 1/2, 1/3, 1/4, like, you do all of those, right? And then if you make it negative, that's going to, in some cases, make it wonky, but in some cases it's going to, like, give you reflections and stuff like that. But when you change the base, all of a sudden you have, like, a whole bunch of different functions that you have to learn how to graph. It can be confusing. Anyway, we're not getting into that stuff too much, but this one's different. So what I would think about this is it's like 3 to the x, but instead of when I put in 1 and I get 3, I put in -1 and I get 3. So I put in -1 and I get 1, 2, 3. If I put in -2, we just saw that, I'd get 9. It's kind of like a reflection. To the 0 is still 1, because anything to the 0 is 1. To the 1 is a third, so I got to get in here a little bit. And then to the 2 is going to be even smaller, and so on. And exponential functions do all have the same kind of look, but the bigger the base, the more like they just really grow fast, shoot up really quickly. Okay, so if I'm going to reflect this one, do the same thing. I went over 1 and up 3, so I'm going to go over 3 and up 1, or sorry, down 1, it was -1. And these points here, this was over 1, up a third. So instead I'm going to go up 1 over a third. And I get something kind of similar in some ways to the other one. Like these guys really kind of, I don't know, look like they're overlapping. Well, let me label these. So this is y equals log base 1/3 x. Any questions? So that says page 451, number 1 to 11. Question 1 and 2. Do AC only. So really getting used to the notation, thinking about what logs are, and a little bit of starting to sketch them and think about how they are related to exponential functions. They're the inverse of an exponential function.